Test, test, test. Can you hear us? Can you hear us?
No more
Hello, hello. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Nah. I can hold it a little bit closer to my face.
We can turn it up. It's fine.
Here, you do a quick test.
Observability can make your life way easier by allowing issues to be spotted and communicate them using pictures. However, most observability tools, cool.
All right. We're just waiting for the light now. All right, and we've got the green light, so we'll go ahead and get started. Hello, everyone. My name is Kevin Howell, and I'm a principal software engineer at Red Hat.
I'm Lindsey Burnett, and I'm a senior software engineer at Red Hat.
So Lindsey and I work together on the Subscription Watch team, which is a team that's responsible for some of the subscription reporting functionality on console.redhat.com. It's a place, for those who may not have seen that yet, it's a web property that you can go to that has some value-added services for RHEL. So if you have a RHEL subscription, definitely check it out if you haven't. Just quick show of hands, I'm curious, how many folks in the audience have heard of console.redhat.com? How many folks have heard of console.redhat.com? Awesome. All right. So here's what we're going to talk about today. We're going to talk a little bit about what Prometheus is generally. We're going to talk through some query basics, just generally how you get some data out of Prometheus with PromQL. We're then going to go into a little bit more advanced stuff. So we're going to talk about some of the functions that you can use in Prometheus, some of the aggregations you can do, ways to query Prometheus, and then finally a couple of other tidbits about ways you can use Prometheus. So first, question that you probably ask yourself is, why should I store data in Prometheus? Or maybe more generally, why should I store data in a time series database? The easiest answer to that is pretty simple. It's monitoring. So if you have use cases where you want to monitor your apps and services, or really anything else, Prometheus is a good use for that. And I'd say, like, specifically, if you're looking at some monitoring use case, Prometheus should probably be your first choice. Prometheus has solved a lot of the sort of problems that you have in the monitoring domain. So things like if a service restarts and you're keeping track of some counter, being able to handle that. If you're trying to look at, if you're trying to report on that counter, Prometheus knows how to handle that. It's also very, very popular. It's super standard in the cloud native ecosystem. And it was, I think, the second project that got adopted into the CNCF. It's pretty broadly used, again, as I said, within like the Kubernetes space, but you don't necessarily have to use it within Kubernetes. And then specifically, our team, just to give you an example, our team uses it for a couple different things. The first is that we use it to monitor our own services. So the components that drive subscription reporting on console. We're keeping an eye on the health of our services using Prometheus. And then one of the other things that we started doing more recently is Red Hat has a few pay-as-you-go services that we monitor those. So we're monitoring customer instances of those pay-as-you-go services, and then using that as the way to capture the usage and then report on that.
Sure. Okay, before we get into some examples of SQL and PromQL, it's important that we kind of level set some definitions. The first being SQL. It's a commonly used acronym for Structured Query Language, which is standardized language for managing and querying relational databases. So you think Postgres, MySQL, SQL Server, Oracle. PromQL stands for Prometheus Query Language, which is the query language used in Prometheus for retrieving and manipulating time series data. The term instant vector is referring to a collection of data points from one or more time series at a specific instant in time. It allows you to analyze the state of metrics at a particular moment. And range vector is a set of data points from one or more time series over a specific time range, and it enables analysis and calculations across the period of time, such as aggregation or rate calculations. So this is kind of an example of what the data looks like when Prometheus stores it. In this example, we've got 4 distinct time series for a metric called HTTP request total. So the first 3 are for successful GET requests to hello world paths. And then the last one would be a time series for bad post requests to the hello world path. So this is kind of the data that the rest of these examples are going to be based on. Each time series here is identified by its associated labels, such as method, path, and code, which provide additional dimensions for filtering and grouping data. And if you want to kind of compare this to what it might look like in a relational database, if we pretend that we have a database table called HTTP requests, and this is what it might look like if every time a request comes in, you insert a record into it so you can keep track of all the HTTP requests. So our first example, that's kind of like the equivalent between SQL and PromQL. On the left here, if you were to do a select star from that HTTP request tables, you'd get all of the results. PromQL, we've got an example of a metric called HTTP request totals, which would return all of the data like the example we just got. So that's just getting that metric back by the identifier HTTP request totals with no filtering. So the next one, we're going to start filtering, and this time we're going to do a select from HTTP request, but this time we only want to see the metrics for the 200 status codes. So what that looks like would be pretty similar from the last one, except only where the code was 200. So you'd get the 3 instead of the 4, because it's filtering out that last bad post request. And then getting a little more advanced, you can do things like aggregation. And so the easiest way to like break down a PromQL query is in the middle. So to recap the first 2 things we learned, the HTTP request total, that's the name of the metric you're querying. It represents the total count of HTTP requests made. The code 200 in the brackets over there is the selector or the filter applied to the metric. It specifies that we're only interested in the instances of HTTP request total where the label is equal to 200. So in other words, it filters the data to consider only requests that had a successful response. And so what's new here is the sum function. And what that's doing for us is performing a summation operation on the metric filtered by the selector. It adds up the values of the HTTP request total metrics for the instances that match that filter of 200. So you put it all together, and what that metric does is it gives us the calculated sum of the HTTP request total metric for all the instances where the response code was equal to 200. It's providing a consolidated count that receives the successful response. And so what it would do, it would add up those values, the 100, 150, and 250. And if my math is right, you'd get a response of the number 500. That's the sum of those 3. Then you can also do some grouping. So similar to the last one, we've got the sum function. So this is going to calculate the sum of the metric HTTP request total grouped by the label code. So this is going to return a vector that has the sum of the metrics for each unique value of the code label. So you'll get two results if you run that PromQL. The first one is going to have the number 200. So for the code 200, and the sum value would be 500. The second result would be that code 400, which the sum value is 75. Now, we'll give it to Kevin, and he can talk about more complicated stuff.
All right, and I'll say as we went along, it gets a little more hand-wavy as we go, because what you'll start to see is that PromQL is a little bit more expressive for certain kinds of operations, specifically like statistical things. This one is still pretty close, but I just want to kind of throw that out there. So with this example, what we're doing is we're looking back in time, and we want to see, specifically some historical data and do something with that. And the way that you do that in PromQL is to do square brackets and then how far back you want to look. You can imagine that this is similar if you were to, in SQL, to have done a query against the timestamp and give it a condition on the timestamp. As I mentioned, some things start to get more complicated in SQL, and this is really where an observability centered tool is really useful. So here, there's a function called rate, and it allows you to very quickly take some historical data points and calculate the rate of change of that metric over the time that you specify. You can do something like that in SQL, but it gets a lot more complicated because you're starting to look at vendor-specific functions and things like that, especially when you get beyond sort of the very basic stuff. And here's where things start to get way more hand-wavy. So in SQL, if you have two different data sets and you're interested in using those two data sets together, you'll use a join. And so in our fictional example, if you imagine you have both that HTTP requests table, and we also have perhaps an HTTP errors table, and maybe we're inserting a record into that errors table every time there is an error for that request, then the way that you're going to sort of combine those two data sets, again, like I said, is the join. And PromQL, you can still do a combination. It's not a join, though. In PromQL, they call this just general aggregation. And the way that works is you have a expression first, and then you have an operation to do on that expression. And that can be a mathematical operation like division, multiplication, addition, subtraction. Or it can be a Boolean operation to perform. Then you have a clause that says how you want to relate the first expression to the last expression, or the following expression, I should say. So in this example, what we're trying to do is we're saying where those two data sets have a common label of request ID, and that will give you this synthesized time series that sort of combines both of them, or a set of time series, really. There is another variant of that that's useful to know about. So the previous example was on as a keyword. There is also ignoring as a keyword. And ignoring also does that relating the two data sets, except that rather than being explicit about what they share in common, you're saying, I want to just assume that everything, all the labels, all of those other attributes in the time series are the same except for whatever you've listed in ignoring. And I'll say generally, you probably want to use on rather than ignoring, because on is a little bit more explicit and is a little more resilient to changes in those attributes. So if you get changes to those metrics over time, say you add more labels to them at some point, then if you have queries that use ignoring, they're more likely to break. But it is an option, and it has its uses. Another scenario that comes up is one thing I did not mention previously was when you do like the general aggregation between the two different sets of time series, they have to have the same cardinality. And if they don't have the same cardinality, then Prometheus will essentially throw an error. There is a way to join two different data sets that have different cardinality, and that's by including an extra clause, and that's group left is the keyword, or there's also a group right. And what the left or right specifies is whether the left-hand side or the right-hand side has higher cardinality. My personal advice here is to start with a query that does not use the group left or group right, and then if you get an error, essentially throw in group left, see if it works, throw in group right if it works. But if you want to be a little bit more deliberate about it, it's really about just checking the cardinality of the two data sets and figuring out which one is higher, and then that's the direction that you apply the group to. So we've talked a little bit so far about the query language itself. The natural question you might ask yourself is, okay, now I know a little bit about the query language. How do I actually interact with Prometheus? And it's essentially the HTTP endpoint is the most common way. There are other ways, but the HTTP endpoint is extremely common. And there are a bunch of different things that you can do with the HTTP API. So a lot of systems that integrate with Prometheus use this. So for example, if you use a tool like Grafana, Grafana is just using the HTTP endpoint for Prometheus. There's also the ability to use any other sort of system that integrates with that HTTP API. And obviously, you can just use curl against it. So the HTTP endpoint for Prometheus is a get to API v1 query, and it takes a timestamp parameter in addition to the actual query. That timestamp parameter is letting you say specifically at what point do you want to grab data from. And depending on what kind of query you actually pass to it, you can get several different types of results. So you can get back a set of metrics for the single timestamp that you passed, and that was what we called, again before, an instance vector. Or if you do something where you're asking for data with one of those ranges specified, then you get what they call a range vector, and again that's just you're getting back data points for multiple timestamps. And there are also some other things that are a little less common. You can but actually get it to give you back a single data point. I'll say one thing is that Prometheus is always going to give you either a string or a double precision floating point number. And here is what a curl to that endpoint looks like. So again, I mentioned you've got a query parameter, and you've got a timestamp. Oh, we did not include timestamp. Whoops. So there should be a timestamp there. Sorry about that. And what you'll get back is some JSON. And the JSON will tell you whether you're looking at a what the data type return from the query was. So in this case, vector means that you're getting an instance vector back. The other type of query that you can do, or other endpoint you can use, is query range. Very similar to query, except that it also it includes three other parameters: a start, an end, and a step. and that allows you to essentially get a bigger view of that data by having it do the query multiple times and giving you results that look across a range of time, thus query range. It's really just doing that query with multiple timestamps. It does the start, it does the end, and then it does intervals in between specified by the step. And this endpoint is only allowed to return a range vector or to give you data from multiple timestamps. Here's an example of a curl statement for that. And the big thing here, the HTTP API will give you a result type of matrix. That is what you get whenever you're looking at the range vector. So in other words, you've got multiple timestamps worth of data coming back. So, quick show of hands, how many in the audience are familiar with views in a relational database? Awesome. Keep your hands up if you're familiar with a materialized view. Awesome. Okay. So recording rules are very closely related, at least conceptually, to a materialized view. So one thing that you can do with Prometheus is if there is a query that you're doing often, either for performance reasons or just convenience, you can define a recording rule. And what a recording rule will do is it will have Prometheus essentially run the query periodically and then save the results in a new data set that you can query by itself. And this is extremely convenient for multiple reasons. Again, performance is a big one. For us, we have a couple of gnarly PromQL queries that it's easier to kind of encapsulate some of that complexity so that when we're trying to query it, we don't have to paste a larger query and then tweak it and hope we don't mess that up. One thing I did want to mention here, if you're looking at Prometheus data, if you see a metric that has colons in the name, that is an indicator to you that it was made with a recording rule. That is a convention in Prometheus, but it's a very widely followed convention. And in fact, I know that if you pull up a data set that was created with a recording rule in Grafana, Grafana will actually show you a hint, an offer to expand that into its definition. So very common thing in that ecosystem. Sort of lastly, I want to give some just general advice for working with Prometheus and PromQL. So early on, when my team started working with Prometheus, we worked with a Red Hat engineer who is core developer in the Prometheus ecosystem. He's since moved on to other things, but Bartek Plotka. And he shared with us a very, very useful technique for analyzing PromQL and documenting it. And it kind of builds on something Lindsey said earlier. So she mentioned it's because Prometheus and PromQL, because PromQL specifically is a query language that is all about expressions, it's best to kind of start sort of with the innermost expression and then work your way outwards. And then the second thing is that PromQL supports comments. So if you use the pound sign, then you can actually you can actually keep comments in your PromQL. And I threw up an example there. It's actually a little blurry. Let me see if I can get a bit bigger view and talk through that real quick. So here, for example, starting with distance covered total, you might leave a comment there that says we're looking at the previous 5 seconds of distance covered, and then working your way outwards. Then we're going to calculate the rate of that over the previous 30 seconds with 5-second samples. That's a syntax that, for simplicity, didn't mention earlier, but I kind of wanted to throw a more complex example up just to kind of talk through. And then we're going to take the derivative of that, which would be velocity, and then we're going to calculate the max velocity over the previous 10 minutes. And you can kind of see how again, working sort of from the inside out makes it a little easier to parse. And I guess the other thing that I put on the slide, but I didn't mention verbally, but I'll go ahead and mention, is you can do multi-line queries, and PromQL is parsed properly that way. So it's best to comment your PromQL, put it over multiple lines, whatever helps to actually make it so that when you come back to some gnarly PromQL query, you're not like, what the heck was I thinking when I wrote this? All right. Lastly, I have a few suggested resources for you. There is actually a Prometheus documentary if you're curious about sort of the history of Prometheus. It was produced by Honeypot. They also did a Kubernetes documentary. Haven't actually watched the Prometheus one all the way through yet, but I really enjoyed the Kubernetes one, so I'm sure it's good. The Prometheus documentation, I'll say, I always find a little confusing to get to. Specifically for PromQL, I dropped a link here for the starting page for PromQL. It's kind of buried in the general Prometheus documentation. And then lastly, there is a good O'Reilly book on Prometheus called Prometheus Up and Running. So if you're someone who likes to read, the second edition of that just got published in April. So that's also a good resource. And that is all we have for you today. So does anyone have any questions? Yes. And I think what I'll do, I'll just kind of walk my way back there and...
Thank you. Yeah, so my question, with certain relational databases, you would sometimes write to an OLTP database and read from an OLAP database for like write-oriented workloads and read-oriented workloads. Does Prometheus have that same sort of separation where you're constantly writing logs to one, and then it may index it differently and you read from another one?
Yeah, so the big thing there's actually a project in the Prometheus ecosystem called Thanos, and Bartek that I mentioned earlier was one of the core Thanos developers. And the point of Thanos is to take Prometheus data and federate it. And I'm not super familiar myself with like the specifics of Thanos, but I would say that is what you would want to look into when you're starting to think about performance and starting to think about, how do you have a strategy for scaling out a very large Prometheus installation. It's something we use internally at Red Hat. Yeah. Other?
Okay, in a SQL database, we use materialized views primarily for speed of results, not to complex the SQL statement. The way you described it is obviously you're using it sort of as a partial SQL statement that you then go ahead and do the rest of the query. And where I'm going on this is that in a SQL database, materialized views cost you. There's expense. And since this is time sensitive, is there a problem with how many of these materialized views that you go ahead and develop?
Yeah, so there absolutely is. And it's essentially storage cost for, that additional data set. So Prometheus is actually written to be very efficient at keeping a lot of different time series. So the number of time series is not actually as big a deal as you might think. There's nuance there. For example, I know that if you have a metric that has a very high cardinality, that's obviously going to cause you issues in querying. It's going to make those queries just naturally slower. But if we're talking purely about number of distinct metrics, that's something that's not as challenging as you might think. But yeah, we have an example in the OpenShift side of things. they store metadata about OpenShift clusters in one data set, and it's one of the largest data sets that we have internally in our Prometheus, and I know that causes some problems sometimes. But again, that's where, for example, looking at things like Thanos is helpful, because then when you do hit those performance problems, you can look at strategies like sharding out. I don't know where Thanos has landed with this, but I know at one point they were looking at things like having a central point that you can query, like a single Prometheus endpoint that would then actually internally federate that query out to underlying instances of Thanos that had the data. And in general, it's pretty straightforward. My understanding, at least, is it's pretty straightforward to actually like push data out generally. So when you hit those kinds of problems, that's an easy strategy to employ, is to essentially say, well, this data set happens to be very large. We'll push it out to its own instance, and thus, not hurt the performance of all these other important queries that are happening.
Thank you. And I follow up on the question Brett just asked early. I understand that Materialize had very good features. I also agree with Brett that had a cost. So in this case, how frequent is the Materialize views get refreshed? Is it real time, since it's a time series data, or do you have certain time intervals?
Yeah. So it's configurable, and I don't recall off the top of my head what the default interval is, but it's either 2 minutes or 5 minutes, and it's essentially making that query that often. So it can also, cost just to do the query. But again, sort of same thing applies there, where any costs you can kind of mitigate by distributing your time series across multiple instances, and that's worked well for us.
So this might be a little weird because I'm not an SQL or database guy. I've spent my life down in the embedded systems and distributed compute. So hypothetical situation, we have 20,000 distributed nodes, and they're all edge compute class, so they're not, probably either ARM-based or like maybe Haswell or Ice Lake, cheaper processors. But we're sampling roughly 400 times a second, and we're storing, and so here's where we're at. So we're running a small time series database on the edge compute, and right now it's InfluxDB. When we settled down on InfluxDB originally because they allowed us to tier up and keep doing aggregated layers all the way back to the core. So I guess from our point of view is we're at a point where now we're evaluating additional time series databases. That's why I saw the Prometheus. Ooh, let's go check it out. But so I guess the question is, how efficient is Prometheus at edge compute level versus tiering back up to, because we're talking about quite a bit of IOPS on those slow-in systems. So we're running like, Gen 4 PCIe disks at the edge. So.
Yeah. So that is one. I don't actually have a good answer for you. I'd say like some things come to mind. So for example, one of the strategies is to let some of those metrics that you're gathering sort of be aggregated at the system level. So sort of those edge devices. Like the general strategy with Prometheus is to go out and scrape endpoints for services to gather those metrics. You can get data into Prometheus in other ways, but that's the most common thing. And when you do that, you're essentially getting a sampling of whatever that metric was every scrape interval, and that one defaults to 5 minutes, I believe, if I recall correctly. So that becomes sort of your level of precision, is that scrape interval of 5 minutes. And some of it, there's strategies in what kinds of metrics you're kind of gathering. So are you doing gauges? Are you doing counters? I, and I'll repeat just in case folks are interested on the stream or whatever.
Basically, we're sampling power quality measurements on generation sources. So 60 hertz US or North American power signal, right? So we want to make sure that we're looking at frequency response very rapidly and then adjusting to say, change the frequency adjustment for grid phase match.
Okay, I'll try to repeat that. So the comment was that the thing that they're measuring is power quality coming in, and they're using that data for things like phase adjustment. And again, you know, probably not the best answer, is not my sort of expertise, but in that kind of problem, I would look to do things like, if there is a condition that you are watching for, and you're able to make use of a metric of how many times that condition has been triggered, then that can become a counter. And then you would be able to store that within Prometheus. Again, your sort of like resolution or precision would be within the like a 5-minute interval. Again, I mentioned that's the default, so you know you can also tune it up or down. I don't know off the top of my head, you know, what's reasonable for like a floor of that. I don't know how well Prometheus performs if you go down to 1 second interval or, you know, yeah. But yeah. Gotcha. Yeah. So to kind of summarize real quick, again, just in case anyone is interested on the stream or the recording, the comment was that their use case, they're doing sort of aggregation at multiple levels, and as they go up, the reports or data is less and less precise. And he gave the example of if you're looking at like data for a region, is that region phase locked or not? Yeah. Any other questions?
Yeah, so the question is like, so you showed like REST API for PromQL, but is there like a more user-friendly, you know, experience, some sort of a front-end tool, you know, similar to like if you're doing like, you know, MySQL, PHP MyAdmin, or pgadmin for like Postgres?
Yeah. So actually, by default, Prometheus does have a web interface, and you can do ad hoc queries there. And that web interface does allow you to do, you know, the multi-line comments, and has also like some code completion even. So you can start typing the name of a metric and hit, I forget whether it's tab or control space, but you can get completion on the metrics. Yeah. Any other questions? All right. Well, thanks everyone for your attention. Thanks for your time.